Hello, this is a revision video for AP Chemistry, Chapter 2, Compound Structure and Properties. As it's a revision video, we just go through the essential information that you need to know. For more detailed explanations and full video lessons, please check the links in the description below. Good luck revising.
Ionic bonding is the electrostatic attraction between oppositely charged ions. It usually occurs between metals, which form positively charged ions, and nonmetals, which usually form negatively charged ions. Be careful, however, because it doesn't have to be between metals and nonmetals. For example, ammonium ions are positively charged and also form ionic bonding with negatively charged ions. Covalent bonding is the electrostatic attraction between the nuclei of two atoms and a shared pair of electrons. When two electrons get shared between two atoms, the positively charged nucleus of each gets attracted to the shared electrons, and this pulls the two atoms closer together. Sometimes two atoms will share more than one pair of electrons, forming double and triple bonds. Single bonds contain one shared pair of electrons. Double bonds contain two shared pairs of electrons, and triple bonds contain three pairs of shared electrons. The more electron pairs there are shared between the atoms, the stronger the bond. Covalent bonds can be either nonpolar or polar. Nonpolar covalent bonds form when two atoms with the same or similar electronegativities bond together. This means electrons in the bond are equally shared between them, and neither atom ends up with a partial charge. Polar covalent bonds form when there is a difference in the electronegativity between the two bonded atoms. The bonding electrons are pulled closer to the more electronegative atom, giving it a partial negative charge, and the atom with the lower electronegativity has a partial positive charge. For example, in hydrogen chloride, because chlorine has a higher electronegativity than hydrogen, the bonding electrons are more attracted towards the chlorine atom, giving it a partial negative charge, and that leaves the hydrogen atom with a partial positive charge, and the covalent bond becomes polar. It's important to remember that ionic and covalent bonding are the extremes of a continuum of bonding. In reality, most bonds exist between the two extremes. The greater the difference in electronegativity, the more ionic character the bond has, and the smaller the difference in electronegativity, the more covalent character the bond has. Exam tip here, remember it is the difference in electronegativity that determines the bond type of two bonded atoms. It isn't the individual electronegativities of the atoms. You can have two highly electronegative elements bonded together, but if the difference in electronegativity between them is very similar, the bond will still have a very low polarity. For example, using Pauling values, we can see that sodium chloride has a very high electronegativity difference between the atoms involved, meaning they exist as ions, and that means we have ionic bonding. Hydrogen chloride has a slightly smaller difference in electronegativity, meaning we have a polar covalent bond, and in Cl2, chlorine, because the two bonded atoms are identical, both chlorine, they have the same electronegativities, and therefore the bond is nonpolar covalent. Ionic and covalent bonds also give different properties to compounds. Ionic compounds typically have high melting points, meaning they're a solid at room temperature. They can conduct electricity when dissolved in water or molten because charged ions are free to move and carry charge, and they form crystalline solids. Covalent compounds, however, typically have lower melting points and are often liquids and gases at room temperature. They don't conduct electricity because there are no charged ions that are free to move, and they usually exist as molecules rather than charged ions. Finally, we have metallic bonding. In metallic solids, valence electrons are delocalized, meaning they aren't bound to any one atom. This means we can imagine we have positively charged metal ions surrounded by a sea of delocalized electrons. There is strong attraction between the positively charged ions and the delocalized electrons, and this pulls them all closer together. Because the valence electrons are delocalized, the electrons are able to move freely through the structure. This helps explain some key properties of metals, such as their electrical and thermal conductivity, and their malleability and ductility. When two atoms form a covalent bond, there is electrostatic attraction between the positively charged nuclei and the shared electron pair. However, there is also repulsion between the positively charged nuclei themselves. As a result, the atoms will arrange themselves to give a bond length that maximizes attraction whilst minimizing repulsion, the most stable arrangement. Bond length is described as the distance between the center of each nucleus. This internuclear distance determines bond strength and bond length. A potential energy versus internuclear distance graph just shows how the energy of two atoms changes as they form a bond. As the atoms move closer, initially attractive forces dominate, lowering the potential energy. In other words, the electrons get attracted to the positively charged nuclei of each atom, and this attraction lowers the combined energy of the two atoms. At a certain distance, the energy reaches a minimum, and this is the bond length. If the two atoms get any closer than this to each other, now repulsive forces between the two nuclei cause their combined energy to increase rapidly. Such a graph can show us the bond energy, the energy required to separate the bonded atoms. It corresponds to the depth of the well from the zero potential energy line to the bonded atoms together. Bond order refers to the number of electron pairs shared between two atoms. A single bond has one shared electron pair and a bond order of 1. A double bond has 2 shared electron pairs and a bond order of 2. A triple bond has 3 shared electron pairs and therefore a bond order of 3. As bond order increases, bond length decreases and bond strength increases. This is because more shared electrons lead to greater electrostatic attraction between the negatively charged electrons and both nuclei. This stronger attraction brings the nuclei closer together, given a shorter bond, and requires more energy to break, meaning the bond is stronger. For example, carbon-carbon single bonds are longer and weaker than carbon-carbon double bonds, which are also longer and weaker than carbon-carbon triple bonds. It isn't just the bond order that affects bond length. Atomic size also does. Larger atoms form longer bonds because their outer electrons are further from the nucleus. When considering the strength of bonding in ionic compounds, it's slightly different because we don't have individual bonds. Instead, we just have electrostatic attraction between oppositely charged ions in all directions. The strength of this attraction or interaction can be explained by Coulomb's law, where the force of attraction is proportional to the charge of particle 1 times charge of particle 2 divided by the distance between the particles squared. And the distance between the particles here is given as the distance between the nuclei of oppositely charged ions. Coulomb's law shows us that in an ionic compound, the greater the charges of the ions, the stronger the attraction between them. And the smaller the ions, so the smaller the ionic radii, the stronger the attraction between them as well. This helps explain why lattice energy in ionic solids increases with higher charges and smaller ions, but that's covered in more detail a little bit later in the course. Exam tip here. When comparing bonding strength in ionic compounds, we use Coulomb's law. And when comparing bond strength for covalent bonds, we use internuclear distance and the potential energy graphs previously shown. Ionic compounds generally have high melting and boiling points, meaning they exist as solid lattices. Highly ordered structures which contain positively and negatively charged ions arranged in a repeating regular pattern. This structure arises from strong electrostatic forces between the oppositely charged particles. In an ionic solid, cations and anions, so positively charged and negatively charged ions, are arranged in a regular three-dimensional grid. The reason for this is because for the solid to be as stable as possible, it needs to maximize attractive forces between opposite charges, so cation to anion, and minimize repulsive forces between like charges, so cation to cation and anion to anion. Each ion is surrounded by multiple oppositely charged ions, helping maximize attraction throughout the solid crystal. You don't need to know the specific different types of crystal structure or unit cells, but you should be aware that oppositely charged ions will always arrange themselves to maximize attraction and minimize repulsion. We can explain the stability of an ionic lattice using Coulomb's law, where the force of attraction between the ions is proportional to their magnitude of charge, so the charges they have, and the distance between the center of each ion. This helps mathematically explain why the oppositely charged ions will be as close to each other as possible, because then the r² part of the Coulomb's law equation will be as small as possible, meaning the force will be as big as possible. The stronger the force of attraction, the more stable the ionic lattice, and the higher the melting point of the ionic compound. The structure of an ionic lattice also helps explain many of the macroscopic properties that ionic solids have. For example, as we've already said, the high melting and boiling points due to strong electrostatic forces of attraction, but also their brittleness. If you hit an ionic solid, you force the layers to shift, and then like charges can get close to each other, and this causes repulsion, forcing the crystal to break apart. Effectively, you force the same charged particles to get close to each other and further away from oppositely charged particles. Electrical conductivity of ionic compounds can also be explained using ionic lattice modeling. In solid state, ionic compounds can't conduct electricity. This is because the charged ions are fixed in place and can't move freely and carry charge. However, if you melt an ionic crystal or dissolve it in water, then now the charged ions are free to move. This means charge can flow through the substance, enabling the conduction of electricity. Remember, for electrical conductivity, charged particles have to be able to move freely. This is also the same for in metallic structures where delocalized electrons are able to move. We often represent the arrangement of ions in a lattice using particulate model diagrams. Here we show the positive and negatively charged ions alternating in a regular 3D arrangement. The ions are shown as perfect spheres, and the sizes are usually approximate to the ionic radius of each ion. However, they are normally drawn with spaces between the ions. This isn't actually true of how the ions are arranged in an actual ionic solid. However, it can get quite complicated to show this, so we normally draw ionic lattices as unit cells, with ions being placed in corners of a cube to represent how the ions are arranged. But please do remember that in reality, oppositely charged ions are touching and are packed as tightly together as possible. Metallic bonding is a strong electrostatic attraction between positively charged metal ions, so cations, and a sea of delocalized electrons in a metallic structure. The outermost electrons in a metal atom have a weak attraction to the atom's nucleus, and this means they can become delocalized and shared between all of the atoms or ions in a metallic structure. The positive ions are arranged in a fixed lattice held together by their collective attraction to the delocalized electrons, which have a negative charge. The metallic bonding model is very useful as it helps to explain some of the unique properties metals have, such as high melting and boiling points because of the strong attraction between the positively charged metal ions and delocalized electrons, electrical and thermal conductivity, because the delocalized electrons are free to move and carry charge and transfer energy in both solid and molten states, their malleability and ductility, because the layers of ions can easily slide over each other without disrupting the bonding, and their luster. The delocalized electrons reflect light, giving metals a shiny surface. Alloys are mixtures that contain at least one metal. They retain metallic bonding, but often have altered properties, depending upon the composition of the mixture. There are two main types of alloys you need to know: interstitial alloys and substitutional alloys. Interstitial alloys form when small atoms, which are often nonmetals like carbon, fit into the spaces between the larger metal atoms in the lattice. For example, steel is an interstitial alloy composed of iron and carbon. The atoms added have significantly different radii to the metal ions in the lattice, and this means the layers of metal ions can no longer easily slide over each other, which makes the solid stronger and harder. Substitutional alloys contain atoms of a similar size, where one atom replaces another in the lattice. For example, brass is a substitutional alloy made of copper and zinc. As the copper and zinc ions in the lattice are of a similar size, the regular arrangement of ions in the lattice remains largely unchanged. The metallic structure remains uniform, and properties are an average of the components in it. Exam tip here: if you are asked to explain the structure of a metallic solid or alloy, make sure you refer to delocalized electrons and positively charged metal ions. For alloys, it's really important you also refer to the type of alloy that it is, interstitial or substitutional. If the atoms that make up the alloy are a similar size, then it will be a substitutional alloy. If the atoms are a different size, it will be an interstitial alloy. Lewis structures or diagrams are a visual tool to represent how valence electrons are distributed in molecules or ions. The main purpose of a Lewis structure is to show which atoms are bonded together and how many bonds exist between them, so whether they are single, double, or triple. We can also show lone pairs of electrons that aren't involved in bonding. When drawing Lewis diagrams, we follow a step-by-step process to ensure that all atoms achieve a stable electron configuration, usually an octet, and the structure reflects bonding as accurately as possible. We count and add up the total valence electrons from each bonding atom. And for polyatomic ions, we add one electron for each negative charge, and we subtract one electron for each positive charge. For example, for a hydroxide ion, because it has a -1 charge overall, we'd have to add one electron to the valence electrons from the oxygen and hydrogen. And for an NH4+ ion, we'd have to subtract one electron, as it has a +1 charge overall. We determine the central atom, which we place in the center of the Lewis diagram. Each single bond that central atom forms to outer atoms contains 2 electrons. And then we distribute the remaining electrons to try and complete octets as much as possible. We start with the outer atoms first, and then place any leftover electrons on the central atom as lone pairs. So for example, with ammonia NH3, the nitrogen atom has a valency of 5, meaning 5 electrons in its outer shell, and each hydrogen atom has a valency of 1, meaning 1 electron in its outer shell. This gives us a total of 8 electrons. Well, we would have 3 single bonds between the nitrogen and hydrogen atoms, represented by 2 dots, and this would leave a lone pair of electrons on the nitrogen atom, shown as 2 single dots. If when we've done this, the central atom doesn't have an octet, we can try and convert lone pairs from outer atoms into bonding pairs to form double or triple bonds if needed. For example, the molecule O2 has a double bond between the 2 oxygen atoms, meaning 4 dots are placed between the 2 atoms in the diagram, leaving 4 electrons on each oxygen as 2 lone pairs each. Although the octet rule is usually satisfied by most atoms with Lewis diagrams, there are some exceptions. Some atoms, mainly in period 2, can be stable with less than 8 electrons in their outer shell. This would be an incomplete octet. For example, BeCl2 contains a beryllium atom that only has 4 electrons in its outer shell in the molecule, meaning it is an incomplete octet. Some elements, usually in period 3 or below, can actually have more than 8 electrons in their outer shell. These are exceptions to the octet rule again and are referred to as an expanded octet. For example, in SO2, sulfur actually has 10 electrons in its outer shell. Exam tip here: always remember to count your total electrons before and after drawing your structure. You'd be amazed how many marks are lost every year because students forget to do this step and don't realize they've made a mistake. And remember, for polyatomic ions, add or subtract the correct number of electrons to compensate for the charge of the ion. Resonance occurs when 2 or more valid Lewis structures can be drawn for a molecule by moving electrons only, never the atoms. These are called resonance structures. For example, when drawing a Lewis diagram for the molecule ozone, O3, we end up with 2 valid structures. If we label each oxygen as A, B, and C, we can see that in the first structure we have a double bond between the oxygen A and B and a single bond between oxygen B and C. And in the second possible Lewis structure, we have a single bond between oxygen A and B and a double bond between oxygen B and C. Now, neither of these is actually strictly speaking correct. The true structure of ozone will be a resonance hybrid, where we have an intermediate bond somewhere between a single and a double bond between both oxygen atoms. And we know this is true because when we actually study the bond lengths in ozone, we only find it has one oxygen-oxygen bond length, whereby if it had a double and a single bond, we would expect two different bond lengths. We see something similar with a carbonate ion. CO32- can be represented with having a double bond between oxygen A and the carbon, a double bond between oxygen B and the carbon, or a double bond between oxygen C and the carbon, with all the other oxygens having single bonds. Again, none of these is actually the correct true structure, and instead the resonance hybrid will be an average of all three, all the oxygen-carbon bond lengths actually being the same. Now, sometimes molecules or ions may have more than one Lewis structure, but some are more valid than others. To determine which is the most valid Lewis structure or most likely, we can use something called formal charge. The formal charge of an atom in the Lewis structure is a hypothetical charge that we assign to an atom in a molecule. We assume that the electrons in all covalent bonds are shared equally between the atoms. To calculate the formal charge of an atom, we take the number of valence electrons it had at the start, subtract the number of non-bonding electrons it has in the Lewis structure, then minus half the number of bonding electrons it shares with other atoms. A preferred Lewis structure will always have the smallest possible formal charges on the atoms, and it will try and avoid the same charges on atoms next to each other. Ideally, more electronegative atoms have a negative formal charge, and the total charge of all formal charges should give the overall charge of the molecule or ion. Because of this, we can determine which is the most accurate Lewis structure for a particular species by looking at the formal charges assigned to each atom in it. For example, if we take an NO2 molecule, we can see there are two ways we can represent this as a Lewis structure. In the first, we can have single bonds between the oxygen and nitrogen, with one lone electron on the nitrogen atom, and in the second, we can have a double bond between an oxygen and the nitrogen, and a single bond between the other oxygen and the nitrogen. Again, the nitrogen has a single unpaired electron. How can we determine which is the best representation? Well, let's look at the formal charges. In the first structure, the nitrogen formal charge will be 5 minus 1 minus 4 divided by 2. Because the valence number of electrons for the nitrogen is 5, because it's in group 5, it has one non-bonding electron, and there are 4 bonding electrons around it, meaning 5 minus 1 minus 4 divided by 2, giving a formal charge of positive 2. The oxygens are both identical here in terms of their electron arrangement, and their formal charge will be 6 minus 2 divided by 2. Because their valency is 6, they have 6 outer electrons to start with, they each have 6 non-bonding electrons, and they each share 2 bonding electrons with the nitrogen, giving a formal charge of minus 1. So in the first structure, we have a positive 2 formal charge on the nitrogen, and we have a negative 1 formal charge on each oxygen. In the second structure, the formal charge of the nitrogen is going to be 5 minus 1 minus 6 divided by 2, because again, the valency of nitrogen is 5 outer electrons to start with. It again has one non-bonding electron, but this time has 6 bonding electrons around it. So therefore, 5 minus 1 minus 6 divided by 2 equals 1. However, in this structure, the two oxygens are different. In the first oxygen, the formal charge is going to be 6 minus 4 divided by 2. Again, a valency of 6, 4 non-bonding electrons, and 4 bonding electrons. This gives a formal charge of 0. In the other oxygen, we have 6 minus 2 divided by 2. Again, a valency of 6 non-bonding electrons this time, and 2 bonding electrons, given a formal charge of negative 1. So which of these structures is better? Well, structure B only gives 2 atoms with a formal charge, whereas structure 1 gives 3 atoms with a formal charge. And the formal charges are also larger in structure A compared to structure B, meaning we've minimized formal charge in the second structure compared to the first, so the second structure B is a better representation. However, remember, it is still only a representation. It isn't a perfect reflection of bonding. As useful as Lewis structures and formal charges are, it's very important to remember that they do have limitations. VSEPR stands for valence shell electron pair repulsion. Core idea is simple. Electron pairs around an atom repel each other, and therefore arrange themselves to be as far apart as possible. This includes both bonding pairs and lone pairs, which together are called electron domains. In order to predict the geometry around a central atom in a molecule, we first of all have to identify how many electron domains surround it. A single, double or triple bond or lone pair each counts as one domain. This number tells you the electron domain geometry. Exam tip here, single, double and triple bonds all count as one domain. If a central atom has 2 electron domains around it, it has a linear electron domain. If it has 3 electron domains around it, it has a trigonal planar electron domain geometry. If it has 4 electron domains around it, it has a tetrahedral electron domain geometry. If it has 5 domains around it, it has a trigonal bipyramidal electron domain geometry, and if it has 6 electron domains around it, it has an octahedral electron domain geometry. Electron domain geometry that we've just looked at includes all electron domains, so bonding pairs and lone pairs. However, molecular geometry only considers bonded atoms, so lone pairs aren't included in the final shape. Now, if you only have bonding pairs and no lone pairs, the electron domain geometry will obviously be the same as the molecular geometry. But if your central atom does have lone pairs, we need to account for these. For example, if the central atom has 4 electron domains but 1 lone pair, then the molecular geometry is trigonal pyramidal, with a bond angle of approximately 107 degrees. Notice the bond angle is slightly less than in a tetrahedral arrangement because the lone pair of electrons repels the bonding electrons more than the bonding electrons repel each other, meaning they're squeezed closer together given a slightly lower bond angle. If the central atom has 2 bonding pairs and 2 lone pairs, now the shape is nonlinear, and the bond angle is decreased even further to approximately 104.5 degrees. And if the central atom has 4 bonding pairs and 2 lone pairs, now the octahedral electron domain geometry becomes a square planar molecular geometry with bond angles of 90 degrees. You also need to know the shapes for seesaw, T-shaped, and square pyramidal. Exam tip here. Always start by figuring out the electron domain geometry around a central atom and then factor in the lone pairs of electrons to determine the molecular geometry. Don't skip that step and go straight to the molecular geometry. Always figure out the electron domain geometry first. As an extra note here, the rules that we use for VSEPR theory also apply to small polyatomic ions, such as NH4+ ions, which are tetrahedral, and NO3- ions, which are trigonal planar. Bond order refers to the number of electron pairs shared between 2 atoms. A single bond is 1 shared pair of electrons and has a bond order of 1. A double bond has 2 shared pairs of electrons and a bond order of 2. And a triple bond has 3 shared pairs of electrons and a bond order of 3. As bond order increases, bond length decreases and bond strength increases. This is because the greater the number of shared electrons between the nucleus of each atom, the greater the electrostatic attraction between them. And this stronger attraction pulls the nuclei closer together, given a shorter bond, and requires more energy to break, meaning a stronger bond. A molecule can be polar or nonpolar, depending on whether it contains polar bonds and the molecule's symmetry. Remember, a bond can be polar if the 2 bonding atoms have different electronegativities. Nonpolar molecules have no permanent dipole, so even if they contain polar bonds, the bonds are arranged so the dipoles cancel out, given a nonpolar molecule. For example, carbon dioxide and tetrachloromethane. Polar molecules, however, do have a permanent dipole. This is because the dipoles in the molecule don't cancel out due to asymmetry, and the molecule is polar. For example, molecules of water and chloromethane. Hybridization is a model used to describe how outer atomic orbitals of an atom mix to form hybrid orbitals used for bonding to other atoms. The hybrid orbitals have equal energy and are orientated in specific geometries to minimize electron repulsion. Hybridization can be used to explain the shapes predicted by the VSEPR theory outlined previously. For example, when carbon forms bonds to other atoms, the outer s and p orbitals can hybridize and merge together. If the s and 3p orbitals all merge, then 4 new hybrid orbitals get formed, which are called sp3 hybrid orbitals. sp3 because they were formed from one s and 3p orbitals. The new sp3 hybrid orbitals have a tetrahedral geometry and an angle of 109.5 degrees between them. Sometimes not all of the outer atomic orbitals merge to create the new hybrid orbitals. For example, for the carbon, if only one s but 2 of the p orbitals hybridized, then 3 hybrid orbitals would be formed, sp2 orbitals, and they would have a trigonal planar arrangement with an angle of 120 degrees between them. And if only the s and 1 of the outer p orbitals hybridized, then the new hybrid orbitals would be sp orbitals, and there would be 2 of them with a linear arrangement and an angle of 180 degrees between them. Because of this pattern, we can very quickly determine the type of hybridization a central atom in a molecule has based on its molecular geometry. If it's linear, that would mean sp hybridized. If it's trigonal planar, sp2 hybridized. And if it's tetrahedral, sp3 hybridized. Outer d orbitals can get involved in hybridization as well, but we don't need to worry about that at this stage in the course. We can classify covalent bonds as being either sigma or pi bonds. Sigma covalent bonds form by the direct or end-to-end overlap of orbitals along the bonding axis between the two atoms. They are present in all covalent bonds, so a single covalent bond will always be a sigma bond. Pi bonds, however, form by the sideways overlap of adjacent p orbitals of two bonding atoms above and below the bonding axis, so they are only found in double and triple bonds. So this means a double bond will contain one sigma bond and one pi bond, and a triple bond will contain one sigma bond and 2 pi bonds. Because of the type of orbital overlap, sigma bonds are slightly stronger than pi bonds. The shared electrons are closer to the nucleus of each bonding atom, meaning stronger attraction that's harder to overcome and break. Pi bonds also restrict rotation around a bond axis. They can't rotate. You should be able to quickly identify how many sigma and pi bonds there are in simple molecules based upon the type of bonds present. For example, in the molecule ethene, there is a total of 5 sigma bonds and 1 pi bond. This is because there are 4 single bonds between carbon and hydrogen, which are all sigma bonds, and there is a double bond between the 2 carbon atoms. Well, a double bond is made up of 1 sigma bond and 1 pi bond, giving 5 sigma and 1 pi bond in total. In the molecule carbon dioxide, there is a total of 2 sigma and 2 pi bonds. This is because the carbon-oxygen double bond is made up of 1 sigma bond and 1 pi bond, and because there's 2 of them, that would give 2 sigma and 2 pi in total.